I'm not sure I'm live. I need to check that. I'm live. Okay. I'm there. I will quickly introduce agenda. Call again should take currently between half hour and an hour. At the beginning, I would like to start with music to add live to this live stream. I've got full permissions from Nigel Mitchell, the author and the composer from Tunnel Mental. I think he from Tunnel Mental and his band Tunnel Mental Experimental Assembly create fantastic music. So yeah, let's build some mood and then we will start the session. Okay, I hope you've built good mood. I need to mention Nigel Mitchell is a British man. He lives in Los Angeles. He's a music creator, composer, and I believe he has a band, Fundamental Experimental Assembly. Yes, I wanted to introduce you to that, and I hope you've built good mood. The next part of agenda is what was in the topic, so high performance computing utilizing CUDA. And actually CUDA toolkit gives the library, this is template library of header files called Trust, and that allow to build rapid prototyping of parallel computing utilizing both host and GPU device. For that we will create the project, of course, with Cmake, and like in previous call, I will create static library that will be based on the CUDA methods that we will be using in our project, and a similar configuration to the previous stream. And if you need to find some information how to install CUDA toolkit, you can switch back to part number 1, the first stream, where I am introducing the steps and where to find that information, and from that you can Google or chat with AI to go through the steps, and you can then quickly go back and experiment with CUDA and Frost. Firstly, I will create the structure of the project. So we'll need the library catalog. It will be my CUDA, and we need the source catalog. And for Cmake, we need Cmake lists files. So I'll create those files. One, and let me copy that to. Okay, and within my CUDA we'll create another folder for includes, and I know that good practice is to have another one with the name of our library. So I will add my code, sorry, not my code, my CUDA, and from my CUDA I will create the header.h, as simple as possible. So currently having the header, and we need to create main.cpp. The name doesn't matter really. It is your choice. For main, I'm using the main CPP. And what next? We need to, actually you can use if not defined, by the other way it's just pragma once. That's what Oliver works. Let's check that, and that will be void CUDA Frost. With Ctrl+Shift+P we go to the menu. We will create information for Visual Studio Code with our include path. I will copy path actually this is what we need. We have that. We will add another folder for sources, and then we will create a new file that will be my CUDA CU. And the extension matters, so for C++ we use CPP extension, for CUDA we use CU. And there we can include our my CUDA / header. And you see that this is the definition is not found, so it's just declare. So let's properly create definition. So the issue is gone. And how about trust? With Ctrl+Shift+tilde I will open the terminal, and let's find where is trust. So you should, when you install CUDA toolkit, cd, it's usually under USR local CUDA target, your target, my machine or architecture, and then okay, let's go there. Includes. So there are libraries that as for CUDA, but Frost, as I mentioned, this is template library. Means there are generic functions of header files. So so usually the code that is used is in that files. So no additional library linked should be there. You go to the Frost and you see what header files it has. So you can check that, of course, and mainly we'll be using the copy header, device vector, and device vector and the host vector. But where is, there is host vector. So this is for rapid prototyping, but also for production applications, systems, because it's optimized and actually it works perfectly. It was built, I think, more than 10 years ago. I saw some dates of 2012, but 2018 is when it was mature, so I believe it is used widely over the world in some real systems, in the science, in laboratories, or yeah, probably on the serious markets. What else? We use the transform, we use sort, and actually NVIDIA Frost is built with the similar design as STL, standard template library of C++. So the vector, the standard vector, is also one of the containers that is widely supported, because well, it it allows contiguous memory blocks. It has random access to the elements, and yeah, it has a couple more features, but I'm currently focused on Rust. So, if I will remind myself, I will mention that. Okay. So currently we have Cmake, and this is our library, Cmake lists. So as in the previous stream, we'll create a library, as simple as that. We'll call it CUDA, and we will provide src / my CUDA cu. So we have just one file for that, and as previously, target include directories. We need to provide the includes for my CUDA, the scope public folder include, and for intrinsics that was enough, but for CUDA we need to specify the CUDA architectures that will be supported. So set target properties for my CUDA properties, and that is CUDA architectures. And what works on my laptop is 5072. Yeah, quite simple. Second part is our Cmake list of the application and the program we built. So this is the root of the configuration. Cmake minimum required version 3.10. About Cmake, you can check the first video, YouTube, Google, AI chat. We will specify Cmake CX6, which is C++. Compiler, that will be ICX. I like it, and yeah, I want to use it more. Project is the next one, our stream number 3. We need to specify languages we will be using. We will set Cmake C++ flags. We don't have any other flags, so we specify just optimization, the Hive optimization. So actually the compilation will take longer, but it will work better. And then we need to just add subdirectory, which is with our Cmake list for static library. After that, we can specify the files that we'll be using as sources, and that will be src main cpp. Then we add executable, so it will be up from our sources. So we refer to our sources variable, and target link libraries for our app, and libraries. Let's we have that scope. We need to add CUDA and my CUDA. Okay, we have main, so we will create main file, and we will include my CUDA header, and then we just call CUDA Frost. I will close that. I will split screen. What else we need? We need one more folder for build. So on the left terminal we will compile, on the right we will run and let's check if everything is prepared. Okay, done. Looks good. So also we can check VCC version. We have CUDA compilation 12.6, and yeah, yesterday I've checked that PyTorch already support that. So yeah, I was also able to create the Python virtual environment with the PyTorch, with Jupyter, and probably you can expect some stream with PyTorch tests. And I'm very curious about the library and CPP. There is other way of working, so I will be checking also the CPP PyTorch. I hope soon. But currently we focus on Frost. So it's there. And actually let's currently implement our functions. So that will be void task number 1. Task number 1. Oh, we need to add CUDA includes CUDA runtime. Include. Yes, there is CUDA runtime. We need IO stream, that's standard one, so maybe I will move that. Include lower, so this is the main part, and then I will copy that. Let's make additional issues so that Frost, no suggestions, probably because I haven't added if I add, and if I, maybe that will boost programming, not that, but again. Oh, come on. Copy. Okay. So host .h. There is CUDA. Interesting. Oh, Frost. Yeah, spelling is very important. What else? Frost without the rust. Device vector. By the way, Rust support intrinsics, so you can check if you're a fan of Rust. That might be great boost to your programs. What we need else? Trust, transform. I will add all to not go here and there. Frost, generate. Frost, sort. Frost, copy. Include. I'll be trying to using import from Nevest CPP, but currently let's focus on the includes. Frost, reduce, Frost, functional for functors. Okay, we will also need C standard library for rand function, which generates random numbers. That's quick way to do that. There are other ways, of course, but let's just do that. And we will do a small short benchmark for the time that operation, at least one operation takes. Okay, and we will create, it's half hour, 2-3 tasks. So first one, I will add comments. So we generate random data on the host. And from the first stream, you know that there is host, which is a CPU with memory, and a GPU device and its memory. And previously on the first stream, we were using a global specifier, and global specifier is to call kernel function. So the call from the host, the code that is on the GPU, and there are two more specifier, which is a device and host. And the difference is that device allowed to run code from device, which is GPU, and host is specified that that routing entry point host will be on the host, and device will be on the device. That shortly we can tell. So host vector, and that will be, so this is generic, so the template, so we'll use integer, and that will be h vec, and we will reserve memory, and we will do that in nice way. So we will reserve roughly 32 mega of numbers, and to be precise, let me open the calculator with the programming mode, and let me type 32. So you see the binary representation. So we have 0, 1, 2, 4, 8, 6, and 32, the fifth number. And if we do left shift, it will do 20 places shift, and we will get that number. So that's 20 places shift to the left, and we can do the same 20 places to the right, and we will go back with 32, but we want actually very large vector, a lot of data, 32 mega numbers. So this is the shortcut actually. First generate, we will generate data, and that will be large numbers currently. And yeah, actually what I'm doing, I'm providing the parameters. That's the end, and we will use our rand. So rand comes from a standard library that is for random generation, and we use the iterators. Begin it point to the first element, and end it point to the element after the last element, means to the empty space of our vector. And this is how iterators works in C++. So first element and after the last element. So not the last element, but after the last element. So that's quite informative. Then we will transfer data to the device. And on first stream we are using CUDA memory copy, and we'll doing more CUDA C. But Thrust is for rapid prototyping, so you will see how to do that with Thrust. So we create device vector, dvec, and we just use assign operator. So that will, we need to specify the type that we work on. Yeah, so with assign operator we transfer data directly, and so device vector class handles the operation. So very simple. Okay, so we have our numbers randomly generated on the device, means in the GPU memory, and currently we can sort data, and Thrust provides stable sort and sort, and I've roughly checked, well, it is similarly based with the same design as standard template library STL, and sort might be more efficient, so I will use fast sort, and we will provide dvec begin, so our iterator, and we specify the end of what we want to do. So actually we utilize the wall, we'll sort every each number, so the wall vector will be sorted there. And yeah, there is one thing, you can go to each of the element of dvec with the subscript, with square brackets of the subscript operator, but the information is that each operation utilizes CUDA mem CPI mem copy, so so you can do that, let's say not extensively, I would say. So to bring back data from GPU to host memory again, we'll use fast, and you see that we use fast namespace. So usually there is STL colon operation or class, and fast is within the fast namespace, as you see. Yeah, the namespace is very important actually. And dvec, so very similar, so you will learn it well. Typing and vector, so this is from, and we want to copy to hvec from the beginning. And what is important, that the size of the numbers is equal. So here we reserve the data. Oh, great! It shows actually how many numbers we will have. I hope you see that. Oh yeah. And actually we have copied that, and let's use chrono to check the time from, let's say, from here. So we use auto start, that will be standard library namespace, standard, we go to chrono, we go to monotonic clock, which is steady clock, and we take that peak. So this is our time point start. The steady clock is monotonic clock. There are different versions, like high resolution clock as well. Shortest tick period, but yeah, sometimes it's better to use steady clock, so monotonic clock. And we just need to tell what is end point. So this is our end, and we need just to calculate duration. So the difference between end and start standard chrono namespace, that is duration cast, and you can cast there to what duration you want, chrono, and that will be milliseconds, and we provide end minus start, and we take count. And I won't be using IOStream, having the live stream. I will use printf. It's task 1 milliseconds, and that is large. That is large numbers, so we need large, long decimal, and new line, and we'll place duration. Whoa. Okay. Copy path. CD. Okay. My user, YouTube, stream free. Okay, clear. Let's cd build make. Let's see if you have first task done with nice examples. Then we'll go to task number 2 and number 3, and that's the end. You see, it takes longer as the first is template library of header files, and we have optimization. So let's run. Oh, so the question is, I haven't called the task number 1 from our code. So that is task number 1. We go task, do not forget, and task 3. Then we'll just implement that. Takes time, so let's call it. Timing is not great because my laptop is busy, so it doesn't have full resources. So actually, I can't show, but there are just 2 digits when I was running that. Without any load on the CPU and memory graphics, but currently it utilizes a lot of resources, so that's why it can be a good benchmark currently, but you can check on yourself. Okay, task number 2. That we'll use reduce function. So for that we will do addition of our numbers in vector, and for that we need to know that we can go above the range of our type, and for that actually we need to modify the random function to give less numbers. Or use long, but for this example I will reduce the numbers and firstly, and then we will reduce to do the addition of numbers in our vector. But long should work actually on 64 bits memory. It is with the limits, namespace and numerics. You can check that. I will include limits, and then from standard numeric limits and numeric limits, you can check long. How it is implemented? Struct. Okay. So auto number. Oh, sorry. Okay. Numeric limits. This max function. Auto max. Okay, and then firstly let's print task number 2, max long max. That will be helpful. Okay, just quickly let's check how large is long on this architecture. Long int format. So if I provide ll, long has type long int. So what's the format for long int? Let's try it. Let me quickly check on. LLU. Should work. U is unsigned. Long unsigned. Let's see. Okay. What was the number? Yeah, that's very large number. So so we can work on the digit, but we will not use it now. But it's very good to know what are the limits, how many data can be stored, what is the data overhead, and such things to be in scope. Actually, that's very important. Okay. So task number 2. We use first host vector of type again int, and that will be hvec of 100 elements, and you can specify that will be 100 elements, each with 0 as well. And we will use first generate again to generate numbers, but we don't want large numbers. I will use just int, not long. So for that I will create the function my rand, and my rand returns everything between 0 and 1000, and for that I will use rand and modulo 1000 to limit the numbers that we have. So modulo is res from the division, in our case by 1000, so it always will give the numbers up to 1000, and I will use my rand. We can print the numbers, but it's not interesting really. So we can, let's say, like always, we can do, okay, let's specify size t and 100, that will be n, that will be n, e plus plus, or actually it should be plus plus I, it works better. And for that actually we use such way, and for that we can use printf. Okay, let's say every tenth, if e %10 equal to 0, printf task var number, and this is decimal of our hvec with the subscript square brackets, but this is the subscript operator. Okay, so what else? We will move like before, so transfer data to device. So we work on the GPU. We use parallel programming with the first library, and then we will calculate the sum of our numbers. So that will be x reduce the vec begin, so first element the vec, after the last element reduce. You can inspect that init, last init, I need to check the arguments that we are passing, but this is how it works. First, and we are, so there are the functors. So functors are the callable. It can also be callable object, the function, or if you need something more advanced, this is I will prepare that. So it's almost 1 hour, so it will be 1.5 probably. But I will play with the pleasure Eternal Flow from Nigel Mitchell, Tunnel Mental, this EP album. You can find tunnelmental.bandcamp.com. There is a lot of music by Tunnel Mental. And so this is our functor. Okay, so we have readers, so we just, again, let's copy, let's print, and task number 2, reduce of x. So we need to place new line, and we place new line. Okay, we are almost done with, we are done with task number 2. Task number 3, there will be portion of math as well, and I will be painting again. Because it is better also to explain and to understand, and for me to follow the logic actually. Let's run. Oh, and task number 1, you see, it was better. Now is so the summation of those numbers. It's every 10. So there is 100 numbers, and we print just 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we print just 10, but we add 100. So reduce actually it's do, and what it does, it calculates on the GPU, not on the host, not on the CPU with the CPU and memory, but on the GPU processor and GPU memory. And you can check the time, but that was example. You can copy the code, and actually you need to write and then copy. Task number 3, and for task number 3, we will work on saxpy function, and saxpy is single precision a times x plus y. This is the function often used. I will put it there as comment. Saxpy is single precision, so y equals a times x plus y, and this is the transformation. I've checked it is used in the digital signal processing. For example, it is used in machine learning, so it do transformations of let's say your function when you have the pair of x and y, and you need to do something with that. So you use the scalar actually, and you are using the multiplication for your x values, and you are adding y value. That's why I will print that, and I will explain and actually provide some useful information about the functions, and a bit about derivative of the function, but more about change of rate. So change of rate between the points that are important for you. Usually you don't have the function, the visual function, but you have the information of the points, and from either from derivative or which is instantaneous, change of rate, or the change of rate, which can be average or instantaneous. Sorry. Problems with spelling, I'm sorry. Instantaneous, and from that you can check if the function is growing, if it's not changing, or has a negative derivative or negative rate of change. But firstly let's do coding, and that will be we will use also the okay, there will be some additional examples, so we need to specify our function saxpy. That will be template. Already I will build the template, so maybe now, maybe I will change later to the template. So that will be float a. We will use device vectors, but also at the same time, so float, so single precision, a floating point. With numeric limits you can check the limits as well, but I won't be doing that right now. And we pass what is not in the C but is in C++, the reference. So actually the alias. So for large objects, passing pointer is it's more expensive, but passing the copy is very expensive, like that. So you are passing the whole the additional version of your device. So with ampersand you are telling that you are passing the reference, so what exactly is in the memory currently. So this is quite important to operate on the references. Like in life, and for that we know that we use the saxpy, so I will copy, maybe that will be there, and we will put it there, and that will be transform. That will be x, what we want to transform. We take x begin x and y begin y end. So we use, and what is important, the range of elements should be equal there. So you need to code or design the algorithm in that way. And we create the functor, which will be struct saxpy functor. It will have constant float a. It will have the constructor. Float a, and we will use initializer. So actually we are copying, the constructor is taking the parameter, and it creates actually our representation of A right there. And yeah, I've mentioned about the host and device specifiers, so information that tells that routing will run either on the host on device, and actually writing can have both. The order doesn't matter, it can be host device, device host. So actually the functor can be used for first host vector and device vector if we specify that, and that will be the callable object. So we return float for our operation, and that will be const float, and we need to specify reference again. Why? That will be const, so it doesn't change the representation. And we return our saxpy. A times x plus y. So this is operation that will be done for each element. Okay. And this is also the callable object with the operator of the brackets. And we need to, the struct and the class actually needs to end with semicolon. And transform will take our functor with a okay. So we have the saxpy transformation prepare, and we are doing for our vectors. So for the references, we have the struct which is the functor, or can be also callable object in different scenarios. We use initializers for the constructor. What is important, a struct is just let's say class with the public data, so everything is public. There is no hermetizations like a private protect. Everything is public with the struct. Okay, that's done. So we implement again from we go through that case, but instead of int we use copying, we use the float. I will not print it here. One example is enough. We use myrand for that, and what else? Because we need to have two vectors, so that will be dvec1, it will be dvec2 of an okay, so dvec we have it. And there is nice function to create the sequence of elements from 0, like 0, 1, 2, 3, 4, 5, 6, 7, and let's use that for generating numbers. Sequence use dvec begin dvec and sorry, so that's initialize to 0, 1, 2, 3, 4, 5 and so on and so on. Okay, then we are able to call our saxpy function that actually do the transformation, so we can call that, but we have defined it that way. So this is the saxpy, and let's say that is our A, and we just put the dvec 1, dvec 2, the references from the names, so directly the alias is there, so we use dvec 1, dvec 2, one for x, one for y. Okay, and lastly we need first to copy from the device memory to the host memory, and we place that at y, the transformation, first last, so everything is stored in y currently, so we use dvec 2 begin dvec and we want to place everything again in our vector h since begin. So it takes on the rest of the elements that we want, and actually then we can print what was done. Every tenth, task number 3, and that will be 3 numbers for the factor. Okay, let's compile. Actually, I don't use CUDA device synchronization. Oh. Yeah, that's the problem. Operator. So you need to specify where this function can be called. Host. So instead of global, to call the kernel from the host to call the device code, we are calling on the host or on the device, and the first take care of that. It's mentioned that calling a host function is not allowed. Error in saxpy operator const is undefined in device code. That's the so we got two errors, but currently it's fine. That's number 3. Okay. So we also print 10 numbers out of 100. And just quick change. So what we can do, we have floats there, but Trust is template library, so we can do same. And instead of float, we tell that we use our type. This is our type. And the same we can do for the struct, for the classes, and the same you can do for the functions. So it will be also the float, but you need to specify the type, because saxpy functor is currently the template. And to run saxpy, you need to tell that you want your type, which is float. And let's compile it again. So you specify, you call the function with your type in the triangle brackets, and you create the template structure for your type. So you can work then changing that to int, having the types on different type. That should be same. Reduce is interesting, that reduce is same. And if I call more times, 50065, now its time is different. By the rounding, it gives Gaussian. Whoa, really? Reduce, let me check reduce again. And let's compile that. So it should be 10,130. If it always generates similar numbers. No, like, and now it gives same. Interesting. Yeah, something that can be checked. Why it always gives. Okay, that's it. I'm not sure if I should paint, but okay, let's do that quickly. Online paint. I was helping myself with the saxpy as well, and well, let's create the axis. So we have X, we have Y, and then we have, let's say there is 1, there is 1. We have that function, there is 2, there is 3, 2, and there is 2. And our function is starts from 0. It has 1, 1 coordinate and 3, 2 xy, so it goes more there. And and yeah, so we want to have y equals ax plus y. So we have two numbers currently, and our I is equal to. So we multiply ax, so 2 by 1 is 2 plus y, so it's 3. Okay, so this is our transformation for that point. And for 2, 3, so we have 2 times 3 plus 2, which is 3, 4, 5, 6, 7. Okay, I planned it better this time. So we have for our x, our y is somewhere there, so our function is like that. And what is important, the transformation is linear, so the function is linear. And what is the meaning of linear here? So there are same changes over the range. It's not like, for example, trigonometric functions, the exponent functions, and the exponent functions, trigonometric functions, the square functions. Those gives different results and are unlinear. And for example, what we have here, we can the rate of change. So over there, rate of change, like previously, is the difference. So this is delta y, and this is delta x, starting from 0. And over there, if we start from that point, this is our delta x, and this is delta y. Delta x, this is y. So this is the rate of change actually. So and how this calculated? I will calculate from between that point and that point. This is the slope. So how steep it is, our function there. So we have, like you know, from the I prime is limes of y, function y, of our x plus delta x minus y of x divided by delta x. So we have there 2 minus 1, 2 minus 1 over, there is 3 minus 1, so we have the result is 1 over 2. This is the rate of change. And what is interesting, when it goes up, so the same like derivative, it is positive when you will have the rate of change from, let's say, like there, we have positive, let's say there we have negative to minus 1. So if you have minus 1 over 3 minus 1, you will have minus 2 by 2, which is minus 1. So you see, if you have just the points and it is the rate of change is negative, the same like and actually for our function this is a, the derivative is a, but this is instantaneous rate of change, but rate of change can be also average, so like for that change between that point and that point, or not specifying that point, but usually it is more of a, and yeah, and if actually it is on that line, so you will see that y is not changing, so it will be like 1 minus 1, so it will be 0, means it doesn't change. Okay, we finish. Let's play music, and I wish you great rest of the day.